In this video, we're going to discuss a very easy rule that will allow us to compute some limits. It's called L'Hopital's rule. And what it says is, if f and g are differentiable, meaning we can find the derivative of these functions, and when you were to try and plug in a, so f of a, it would equal g of a, and both of these would be 0, and the derivative of g for a is not 0, then what we can do is take this limit as x approaches a and plug a into the derivative of f over the derivative of g. So here's really essentially the idea. If you were to evaluate the limit by plugging in a and you get 0 over 0, take the derivative of the top and bottom and plug in a. So let's see how to use this in a couple examples. We're going to evaluate each one of these limits. So let's say I want to evaluate the limit as x approaches 0 of sine of x over x. Well, sine of 0, if we plug in 0 for x is 0. Sine of 0 is 0. So we get 0 over 0. So in this case, we're going to use L'Hopital's rule. We're going to do the derivative of the top divided by the derivative of the bottom. So the derivative of sine of x is cosine x, and the derivative of x is 1. Now we plug in 0, cosine of 0 over 1. Cosine of 0 is 1, so we get 1 over 1. In other words, the limit as x approaches 0 of sine of x over x is 1. Alright, let's do another example and see how that works again. Let's say we wanted to plug in 1 to this. You'd get 1 squared plus 3 times 1 minus 4 over 1 minus 1, which gives us, on the top you would get 0, and on the bottom you would get 0. So here we can use L'Hopital's rule. So let's take the derivative of the top, which would be 2x plus 3, and the derivative of the bottom, the derivative of x minus 1 would just be 1. And now we can plug in 1. 2 times 1 plus 3 over 1 is 5 over 1. So in other words, the limit as x approaches 1 of x squared plus 3x minus 4 over x minus 1 is simply equal to 5. Alright, let's try it here. The limit as x approaches 0 of sine of x over e to the x, that equals sine of 0 over e to the 0. Now be careful, here we don't actually need to use L'Hopital's rule, and here's why. Well, sine of 0 is 0. However, anything to the 0 power is actually 1. 0 divided by 1 is 0. So we don't need to use L'Hopital's rule in this instance. You only use the L'Hopital's rule when you get 0 over 0. So let's try this one now. Limit as x approaches 1 of natural log x over x minus 1. If I plug in 1, I get natural log of 1 over 1 minus 1. Natural log of 1 is 0, so I get 0 over 0. Here we are going to use L'Hopital's rule. The derivative of the natural log of x is 1 over x. The derivative of x minus 1 is 1. If I plug in 1, I get 1 over 1, which is just 1. So the limit as x approaches 1 of natural log x over x minus 1 is 1. Here are two more instances where we can apply L'Hopital's rule. The first one, if you try and plug in some value and you get plus or minus infinity for f of x and g of x. And that doesn't just limit itself to a simple value. You can plug in infinity also and use L'Hopital's rule for this one here. Or if you try and plug in infinity and infinity to both of them and you get 0, then you can also apply L'Hopital's rule. So basically, if you get infinity over infinity or 0 over 0, you can apply L'Hopital's rule. So let's see how this would work. Okay, in this example, if I tried to plug in infinity, I would get infinity squared minus 4 over 3 times infinity squared plus 5 times infinity plus 1. Either way, you'd get simply infinity over infinity. Now, you may remember we actually did questions that look like this way back when we were doing limits, and we did them algebraically. And what we said was if the degrees are the same, you should get the coefficients. So if you remember, we said this thing here should be the same thing as the coefficients, which would be 1/3. Let's see if that's the case using L'Hopital's rule. So taking the derivative of the top and bottom, we're really doing the limit as x approaches infinity. On the top, we'd get 2x. On the bottom, we would get 6x plus 5. You're thinking, well, if I plug in infinity, I would still get infinity over infinity. If that's the case, because it's still infinity over infinity, we can repeat the rule again. And now we're going to do the limit as x approaches infinity of the derivative of the top. Well, the derivative of the top is 2. The derivative of the bottom is 6. 2 over 6 is just a constant, which is 1/3. So we get what we would expect, which is 1/3.